Answer, okay? Note down and raise your hand. Noted. Example number two. Next question. Example number 3. Example number 3. Just a minute. Try it. The density at atmosphere at the sea level is 1.29. Assuming that it does not change with the altitude, then how high the atmosphere will be extended? Density of the air is 1.29 at the sea level. Density is 1.29. We know that the atmospheric pressure, how much you know? That we know at this point. But pressure we know at the sea level. Atmospheric pressure, that we know. Is this much meter will be the height of the atmosphere. Okay. If you are written, you note it down. And raise your hand.
Recording in progress.
Now we'll move to the next problem. Okay. Next question. We'll go to the next problem. 10.4. What is at what depth of at a depth of 1,000 meter in a ocean? What is the absolute pressure? What is the gauge pressure? Find the force acting on the window of area 20 into 20 of a submarine at this depth, interior of which is maintained at sea atmospheric level atmospheric pressure. We can solve this easily. Thousand meters in an ocean. What is the absolute pressure? Gauge pressure will be rho gh. Absolute pressure will be rho gh plus P atmosphere. P atmosphere you can put the value, rho value you can put GH, height is 1000 meter. So 10 to the power 5 plus 10 to the power 7, 5 again. 3 plus 3, 6 plus 1, 7. This is the answer for the absolute pressure. Gauge pressure only, gauge pressure if you want only rho GH. 10 to the power 7. Okay. Find the force acting on the window of the area 20 centimeter, 20 centimeter. Force is equal to the interior of which is maintained at the sea level, atmospheric pressure. So force will be equal to, because inside the submarine, interior is atmospheric pressure, outside is atmospheric pressure plus rho gh. So net pressure is rho gh, right? So net pressure will be rho gh, pressure into area. So rho gh, pressure into area. Okay, so rho gh into area. So rho gh, rho is then again same thing. Okay, into area. Area also you should put in meters, meter square, 0.2 into 0.2. Okay, that is the area. That's all. That is the force. Okay, clear? Okay, note it down if you want. Okay, then we will do the next problem. Note it and raise your hand. Okay, now coming to question number 10.5 and 10.6. Question number 10.5. Two syringe of different cross section, just like this, filled with water and connected to the tightly fitted rubber filled with the tube. Like this only, maybe two syringe and all. Okay. Diameter of the smaller and larger piston is given. Find the force exerted by the larger piston when the force of 10 Newton is applied to the smaller piston. Okay. Whatever the force is applied on the small piston, the same force will apply on the large piston also. That is a Pascal law. So force will be same only. Okay. 10 Newton force only. Force of 10 Newton is applied to the smaller piston. Okay, it is pressure will be same. Okay, not the force, pressure will be same. P1 equal to P2. So force F1 upon A1 equal to F2 upon A2. Okay, so first force is 10 Newton applied on the smaller piston, right? So smaller piston, pi r square, pi r square or pi d square by 4. That is the area. F2 you have to find out area of the larger piston, 0.03 square by 4. Okay, that's all. You have to solve it. like this: P1 equal to P2, F1 by A1 equal to F2 by A2, 10 by is equal to force by area. So this will cancel. So force you can find out. Newton. 90 Newton is coming here. 90 Newton only, correct. Okay, like that you can find the force. Then what they're asking, if the smaller piston is pushed in through 6 centimeter, how much does the larger piston move out? Okay, so because water is incompressible, total volume will remain same. If this moves this side, that moves that side, so total volume will remain same. Okay, volume will not change because water is incompressible. Okay, so volume L1 into A1, length into L2 into A2, like that. This will be same. Whatever volume change here, the same volume increase there, volume decrease here, whatever volume change there. Okay, if it is moved by how much, smaller piston is pushed by 6 centimeter, 6 into area, like that. Okay, that into this one you can put as x, like that. You have to solve. Pi will get cancelled. X equal to 6, 6 into 1 upon 3 square, 6 by 9, 0.67 centimeter. Okay, clear. 0.67 centimeter it will move. Is it clear? Note it down and raise your hand. Note it and raise your hand. Okay, over now. Now next question. Question number 10.6. In a car lift, compressed air exerts compressed air exerts force F1 on the small piston having radius of 5 centimeter. This pressure is transmitted to the second piston of radius 15 centimeter. If the mass of the car to be lifted is 1300, calculate F1. Okay. Whatever the force you are applying, that pressure will be same. Pressure P1 equal to P2. So F1 upon pi r square is equal to pressure P1 equal to P2 now. Second car is of the mass 1350, so you want to lift it up. So mg is the weight of you have to lift up, and radius is 15 centimeter. So like that you have to do. Pressure necessary, na? So you can first find the F1, then you can find the pressure. Okay. First they are asking to find F1. Pressure you can easily calculate by F1 by A1 formula. Okay. If you have cleared, note it down please. Afterward you can solve at home. Okay, note it and raise your hand if it is clear. Noted now. Example 10.7. Blood velocity. The flow of the blood in large artery of an unassociated dog is diverted through a Venturi meter. Venturi meter is a device to measure the flow. Okay, that's all. Wider part of the, actually it will be like that. So wider part of the meter, Venturi meter. Cross section area 8 millimeter square. Narrow part has an area of 4 millimeter square. Pressure drop, the pressure difference P1 minus P2. Pressure drop in the artery is 24 Pascal. What is the speed of the blood in the artery? Speed they're asking. Okay. Area they are given, pressure they are given. They are using the Bernoulli equation. Okay. Bernoulli equation and some other derivations they are using. Okay. Check this one. I have not taught you that Venturi meter concept. First, I will teach you, then you can use this formula in this question. Okay. So that Venturi meter concept I will teach you. Okay. What is happening in Venturi meter now? You have there is a flow. Okay. This is a Venturi meter. This is the pipe. Venturi meter is fitted in the pipe. Venturi meter is used for measuring the flow through the pipe. It also has a U-tube manometer like this, which tells you the pressure difference. It will have a manometric fluid inside it. It has a manometric fluid inside it. And wherever the pressure is more or less, accordingly the manometric fluid will rise up and on one of the limbs and will go down on the other limb. The difference in the height will tell you the pressure difference in between the 2 points. Okay. Whatever the height difference is coming, that will indicate the pressure difference. The rho gh will be the pressure difference between these two sections, this section and this section where this U-tube manometer has been fitted. Okay. So if you apply the Bernoulli equation between section 1 and 2, P1 by rho g V1 square by 2g, Z1, P2 by rho g, V2 square by 2g and Z2. Z1, Z2 are equal because both are at the same height. P1 minus P2 upon rho g is equal to V2 square minus V1 square by 2g. Okay, this is thing one thing. Second thing is you can even apply the continuity equation A1 V1 equal to A2 V2. Okay, like that you can also apply the continuity equation. Okay, that also you can do. And if you want to find V1, you can express V2 in terms of V1 everywhere because A1 A2 are known. Here also you express put the V2 in terms of V1 from that equation. So you will get a A1 V1 by A2 whole square minus V1 square upon 2g. Then you can readjust and find the expression for V1. So finally V1 will come out to be root over 2 rho gh. This is the formula, right? And one more thing, that this P1 minus P2, what is the P1 minus P2 is equal to rho m gh. Rho m is the manometric fluid density and rho is the density of the actual fluid which is flowing through is, right? So what you are seeing here, it will be P1 minus P2 can be put as rho m gh. Gg will get cancelled. So finally V1 expression for V1 will be root over 2 rho m gh upon rho. If you readjust the terms into capital A by small a whole square minus 1 power 1 by 2 into capital A by small a whole square minus 1 power 1 by 2 minus 1 by 2. Okay. So this kind of formula you will get for V1. Capital is the cross section area of the small a is the cross section area of the point 2. So you will get a formula for V1 using these concepts. Okay. Understanding, or one more time I can explain you if you want to. This Venturi meter, this is a pipe Venturi meter has been put to measure the flow, and to measure the pressure across the Venturi meter, a U-tube manometer is put here. There will be a difference in the level of the water in the U-tube manometer. That difference H, if the pressure difference will be P1 minus P2 will be rho mgh. The flow is happening like this. Okay, so we can apply the Bernoulli equation because as per the law of conservation of energy, the total energy at 1 will be equal to total energy at 2. So Bernoulli equation at 1 P1 by rho g plus V1 square by 2g plus Z1 equals to P2 by rho g plus V2 square by 2g plus Z2. Z1 Z2 get cancelled and P1 minus P2 by rho g is equal to V2 square minus V1 square by 2g and A1 V1 equal to A2 V2. So V2 is equals to A1 by A2 into V1 and P1 minus P2 is rho mgh. Rho m means manometric fluid density. Rho is the density of the normal fluid. And V1 A1 by A2 whole square minus V1 square upon 2g. If you solve this, you can get an expression for V1 is equals to that only I told you root over 2 rho mgh upon rho, root over 2 rho mgh upon rho, and into capital A by small a square power minus 1 by 2. This becomes the final formula for the finding the velocity at 1. Okay, is it clear? Note it down please and raise your hand. After noting, raise your hand. Noted. Okay, Ellen. Noted. Now come to the next question. Same question you can solve now using this concept of formula. You can apply and solve it easily. Same question you can solve just by applying the formula. They apply the formula here only. Root over whatever the formula. Okay. Here the things are given here. Root over 2 rho mgh upon rho into a1 by a2 minus 1 power minus 1 by 2. Okay, put all the values. Rho m manometric rho mgh is the difference in the pressure. Delta P given 24 upon rho. Rho is also given 1060, and this is only solution only. This is also upon inside the root only. Power minus half now means it is inside the root. A1 by a2 whole square minus 1 actually. So a1 by a2 ratio is 2 meters square. So a1 by a2 whole square minus 1. This one. So this is the answer. Okay. This also you can note down and tell me. Then we can go ahead. Okay. In this only formula you have to put. Okay. You can try and tell me. Okay. Okay. Now next question you see. Example 10.8. A fully loaded Boeing aircraft has a mass of 3.3 kg, 10 raised to 5 kg. Its total wing area is this much. It is in the level flight with a speed of 960 km per hour. Estimate the pressure difference between the lower and the upper wing surface of the wings. Estimate the fractional increase in the speed of the air on the upper surface of the wings related to the lower surface. Okay. So already first they are asking the pressure difference. Huh? between the upper surface and lower surface of the wings. Okay. So pressure difference now that given this concept also, weight of the Boeing aircraft is balanced by the upward force due to the pressure difference. Okay. So basically the weight is taken care by the pressure difference of the between the wings, between the two parts of the wings, upper part and lower part. Okay. So whatever the pressure difference that is into area, that is only the weight of the aircraft. From that you can find the pressure difference. Okay. Estimate the fractional increase in the speed of the air on the upper surface of the wing related to the lower surface of the wing. I don't know from where they are using this formula. You can use some Bernoulli's equation or something. P1 by rho g, V1 square by 2g, P2 by rho g, V2 square by 2g. Okay, we can use this equation and solve it. P1 minus P2 is already known. Okay, P1 minus P2 is already known. Using this one we can do actually. P1 minus P2 is known. Okay, V2 square minus V1 square only we have to find out. Okay. Fractional increase only they are telling that, that's why they are writing V2 square minus V1 square as V2 minus V1 and V2 plus V1 like that something when they are solving it. Okay. Average velocity they are using that 960, no, that V2 plus V1 they are using 960 upon 2. Okay. V2 plus V1 upon 2, that is average velocity they are taking as 960. So that's what they have done. I will explain you how they have to do. So first we will write now Z will get cancelled, Z will get cancelled. Okay, P1 minus P2 is known quantity. Okay, rho G, G will also get cancelled. Rho is also known quantity. V1 plus V2 by 2, this is a V average. That is 960, you can use it V average. Okay, so V2 minus V1 is equal to whatever upon V average. You can find the V2 minus V1. Okay, and even you can divide it by V average both sides. So V2 minus V1 upon V average also will come. That only they're asking. We estimate the fractional increase in the speed of the air. This only they're asking here. Okay, so like that you can solve. If you're not understood, one more time I will explain you. This value P1 minus P2 is known value. G will cancel. Rho is known. Divide by V average square on both the side. This is already V average. Divide by V average square on both the side. 1 V average will get cancelled. So V average is also given. This is known, this is known, this is known. So you can find V2 minus V1, that only they are asking. How much the velocity is increased? This only they are asking. Okay, fractional increase. Okay, clear? If you're clear means you note down please. Solve and raise your hand. Okay, note it down and raise your hand. If any doubt, also ask me, okay? Noted? Next question. 10.10. This terminal velocity concept also I forgot to tell you here. This concept also we have to discuss. Concept of terminal velocity. This concept we forgot to discuss. And 10.9, question number 10.9 also. Now we can discuss first. Example 10.9. You read the example 10.9 now. A metal block of mass of area 0.1 meter square is connected to a 0.010 kg mass via string that passes over an ideal pulley. A liquid with a film thickness of 30.3 millimeter is placed between the block and the table. When released, the block moves to the right with a constant speed of 0.085 meter per second. Find the coefficient of viscosity of the liquid. Okay. So what is the force acting on the block? I think that is the weight of the ball is acting on the block. That is the force acting on the block. It's a shear force. And there is a film of the liquid between the block and the surface. That film, actually we are talking about that one. This film here. This place. Okay, liquid film is formed. Thickness also given 0.30 mm. So if you talk about this block, the force acting on the block is the weight. And this is a film. The distance is whatever that is 0.3 mm into 10 raised to minus 3 meter. And this distance and the velocity also they have told, or what? Find the coefficient of viscosity. Speed also given 0.085 meter per second. So 0.085, and this is 0. So force, you know that formula is shear stress is proportional to shear strain. So if you remember the formula, this was the formula. Okay, you have to put all the values here. Weight of the block 0.010 kg mass na mg. Area of the surface. So area of the surface also given 0.1 meter square. Mu also they are asking, find the coefficient of viscosity. Velocity 0.085, and the distance between the two layers, that is 0.3 into 10 raised to minus 3. Using this one you can find the value of mu. Okay, clear? This is the formula. We have put everything and you have to solve and find the value of mu. Okay, note it down if you understood. See that if you are understanding or not. If any doubt, ask me. If you understood, noted now, raise your hand, okay? Noted, Nishant. Okay, next one, next question. Question number 10.9 we have done now. 10.10. 10.10. That only I have to teach you that the concept of a terminal velocity first. Then we can do that question. Stokes law. That I have to teach you. Stokes law. Then you can do the 10.10 question. Stokes law we have to do. So I'll explain you very easy only. Okay. I'll explain you the Stokes law. If any object is falling in the water, okay, a ball is falling on the water. Two forces act on the object. One is the buoyant force which is acting upward. Okay, buoyant force is trying to pull upward, and another force is the viscous force. Viscous force. Okay. And another force is the weight of the object. So that is what weight of the object. Buoyant force is acting, and viscous force is acting, and then viscous force is also acting in the upward direction, and another force is the weight of the object. Okay, three forces are acting on the object. Okay. One is the weight of the object which is acting downward. Another is the buoyant force which is acting upward. Another is the viscous force which is acting upward, opposing the motion. In fact, the buoyant force plus the viscous force, that is the weight of the object. That should be the weight of the object. At one point of time, this will happen. That buoyant force plus viscous force will be the weight of the object. Okay. That time the object will attain the uniform velocity. First, initially velocity will increase, so velocity will decrease, but it will attain the uniform velocity, and then it will not decrease further. Uniform velocity will be there. Okay. So uniform velocity. What is the buoyant force? Is nothing but there is a force applied by the water on the object. How much that force is? There is volume into density difference. Okay. Volume of the object 4 by 3 a cube into density difference. Density of the object minus density of the water. Okay. Density into volume mass. Okay. Mg plus this is volume. This is the density difference. This is g plus viscous force. Viscous force will be 6 pi eta av. 6 pi eta av. Eta is the coefficient of friction, I think. Okay, eta is the coefficient of friction. Okay, small is the radius of the object, v is the velocity of the object. This is Stokes law. Okay, this force, viscous force. Okay, that is equal to the weight of the object. Sorry, here buoyant force will be equal to density of the fluid. Okay, and here that is equal to weight of the object. Weight of the object is sigma is the density of the object. Volume into density. Okay, into g. This is the equation. Okay, for finding the velocity, final velocity. Okay, you can observe the equation. I can explain you one more time if you want. Okay, if you want, I will explain you one more time. Buoyant force plus viscous force equals to weight of the object. Buoyant force will be equal to volume into density of the liquid, and volume of the object, density of the liquid. Okay, into g plus viscous force will be 6 pi eta a. Viscous force will be 6 pi eta av. Okay, is equal to weight of the object, volume into density of the object, sigma solid object into g. This is the formula for finding the final velocity. Okay, from this formula you can find this small v velocity. Okay, note it down. Complete it and then raise your hand, please, if it is clear. Okay, noted, Ellen. So next example 10.10 is based on the same thing only. Terminal velocity of the ball of radius a value is given. Temperature is given. Velocity is also given. Density of the oil is given. And the density of the copper is also given. Okay. So you just put everything in that formula. The formula which we have written, 6 pi eta AV plus 4 by 3 pi into rho cube. Formula everything. Put everything in this formula. They're asking you the what they're asking? Viscosity, na? This is viscosity only. In this, you can, other things, you can fill it and solve it, okay? Solve it home. A value, in meters, velocity in meters. A value, and sigma minus rho is also given in the problem. Solve it yourself, okay? I'm leaving this question. You solve it yourself at home, okay? So next, any other question? 10.10. 10.11 is there. What we can do? Okay. That's the last question, I think. Okay. 10.12 is also there. Flow rate from the tap of the diameter 1.25 centimeter is 0.48. Coefficient of viscosity is also given. After some time, the flow rate is increased to 3 liters. Characterize the flow. Characterized the flow. That means you have to find the Reynolds number, I think, for both. Reynolds number, if you find, you can tell which type of flow. They're asking you the Reynolds number only, okay? Reynolds number calculation. Reynolds number calculation you have to do. Same formula. Rho VD by mu. This is the formula for Reynolds number. Okay. All the values are given, I think. Only velocity. Velocity is Q by A, you know or not? Q is the flow. So first the flow is 0.48. Liters you can convert into meter cube. 10 raised to minus 3. Q by A. Area. Area is pi into 1.25 square by 4. And 1.25 also you have to convert into this one. Like that. Okay. This is Q by A. Then diameter value you have to put. Okay, 1.25 into 10 raised to minus 2 again. Upon mu. Mu also 10 raised to minus 3. Once you know all these things, you can find the Reynolds number for both the cases. Okay. So I will derive one formula for you. You can substitute in that formula. Okay. This type of formula, if you can derive, then you can easily put the values and get the answer. Okay. Getting it noted down, please. Then put the value at home, actually. Okay, clear. Now next question, 10.11 over na. 10.12 last, based on surface tension. That question is based on surface tension. 10.12 and capillary, I think capillary action. Just you can see that only capillary height calculation. I think this one. The lower end of the capillary tube is this one is dipped in 8 centimeter below the surface of the water in a beaker. What is the pressure required in the tube in order to blow a hemispherical bubble at its end in the water? Pressure inside the bubble they are asking, I think. I think in this case, the bubble is inside the water now, so only one side, only air is there, not two sides. So the pressure to be considered only 2 sigma by r, not 4 sigma by r, excess pressure. Okay. Simple question only. Bubble formula only, excess pressure formula you have to apply here. Okay. And excess somewhat lower end of the capillary tube of the diameter is dipped in the 8 centimeter. Is dipped 8 centimeter below the surface of the water in the beaker. What is the pressure required in the tube in order to blow a hemispherical bubble at its end in the water? Okay, you try this question yourself. Okay, one time you think about it, then we can discuss it. Okay, they have done this, solved it or nothing, but there is a 8 centimeter column of water. Na, that much pressure also they are considering. Okay, rho gh plus 2 sigma by r. That formula they are using. Rho gh plus 2 sigma by r. That will be the pressure in the bubble. That much pressure is required to break the bubble. Okay, X. This is the pressure inside the bubble. Okay, this plus this total pressure. Rho gh plus 2 sigma by r. You just try and think on it. Okay. Now we leave this question. You just think on it. Okay. This is this much pressure. Rho gh plus 2 sigma by r. Rho value, g value, everything is there here. Okay. Put all the values and you will know the total pressure. And excess pressure is 2 sigma by r only. because not 4 sigma by r, because outside it's water only, not air. Okay, outside the bubble. Okay. Okay, R. So we take a 5 minute break. Okay, 5 minutes, then we'll start the new chapter. Okay, thermodynamics chapter will start. Okay, after 5 minutes. Okay. You all, both of you are there. Shall we start the chapter? Can you raise your hands? Okay. So we will be covering all these topics, okay, which are written here. Maybe mostly we'll cover the chapter, okay? So I'll go as per your book only, okay? One by one. First topic is system and surrounding. So first of all, I will explain you what is thermodynamics. Thermodynamics nothing but first before understanding thermodynamic system, what we study, what we are studying, that will be system. Suppose we want to study the tube light, so tube light becomes a system. If you want to study the some amount of gas which is inside the container, then that gas becomes a system. So whatever we are studying, that becomes system, and everything else other than that system is surrounding. Everything else other than the system is the surrounding. Everything else other than the system is the surrounding. Everything else other than the system is surrounding. Everything else other than the system is the surrounding. So this gas is a system, and other than that, everything else is the surrounding. This is the system, and other things are surrounding. Okay. What we are studying is a system. Other than that are the surrounding. Okay, noted. Noted. Then raise your hand. If you have noted, raise your hand. Okay. You can see the screen now. No. I'll reshare the screen. Okay. Now can you see Ellen? Yes, note it down and raise your hand. Okay, noted na. Just to wait 5 minutes. Okay, 1 minute. I'm coming. So this concept is clear: system and surrounding. Now next concept. Now one more example I'll give you for system surrounding, like a cup of tea. A cup of tea. If you consider it as a system, so the cup of tea is a system. The tea inside it. So everything outside is a surrounding. And system plus surrounding is called universe. So now basically in thermodynamics, now we are going to see the heat interaction between system and surrounding. Now it is heat, its temperature is more, maybe 70 degree. Hot cup of tea. Outside temperature maybe 30 degree. Air. So how the system and surrounding are going to interact? The heat will travel from high temperature to low temperature. This energy which is contained by the cup of tea, that will travel from high temperature to low temperature. The air will get heated up. The tea will get cooled down. Tea will get cooled down and air will get heated up. The outside air will get heated up. This tea will get cooled down. So heat travels from high temperature to low temperature. Heat travels from high temperature to low temperature. Okay. Heat travels from high temperature to low temperature. Okay. Is it clear? After some time, what will happen? This temperature will decrease and this temperature will increase. This 30 may become 40, 70 may become 60. Then 40 will become 50. This 60 also may become 50. Once both the temperature are equal, the heat transfer will stop. If both the temperature are equal, heat transfer will stop. If both the temperature become equal, heat transfer will stop. Okay, clear? If both the temperatures are equal, now heat transfer will stop. Okay. This is type of things that we are studying in thermodynamics. Okay. I'll give you one more example. This you have noted. If you have noted, raise your hand. I'll give you some more examples. Noted. Please wait for 2 minutes, okay? Just I'll come back 2 minutes. Please kindly wait. Okay, so actually what we do in thermodynamics, I will try to explain you in concise so that you can get an idea of the subject. Basically, we deal with gases. Okay, because gases are compressible. So we will talk about the property. What are the properties? Like pressure of the gas, temperature of the gas, and volume of the gas. These are the basic properties we talk about in thermodynamics. Property means characteristics, properties of the system, which the things which define the state of the system. The value of the properties define the state of the system. For example, your face. Okay, the size of the eyes, the size of the nose, the shape of the ears. These are all the properties of your system or properties of your face. Am I correct? Properties of the face. If you just smaller your eyes or change the shape, size of the nose or something you do with the ears, means the expression of the face will change, right? Expression of the face will change. That means state of your face will change, right? Maybe you are going from happy to sad. Okay. So when you change the value of the properties of the system, the state of the system changes. Okay. Now, how can you change the property of the system? For example, if I want to change all these dimensions of your face, I have to slap you or I have to make you happy. Something I have to do on you. Then your properties of the system will change. Then your state of the system will change. Likewise, if this is the gas, if this is the gas, and if you are trying to compress the gas with the help of this piston, then volume of the gas will reduce. Volume of the gas will reduce. Pressure of the gas will increase. And maybe temperature of the gas also will increase. So basically you are doing work, you are supplying work, or you are doing work on the system. You are doing work on the gas. There is some force and there is certain displacement. There is certain amount of force and certain amount of displacement which is doing the work on the system. So if you do all this thing, work on the system, volume of the gas will reduce, pressure of the gas will increase, temperature of the gas will increase. You can also change the property of the system by heating it. If you are heating the gas, then automatically gas will expand. So volume of the gas will increase, pressure may decrease, and temperature may increase. So you can change the properties of the system by two things. One is doing the work on the system or heating the system or cooling the system. These are the two forms of interaction which you can have between surrounding and system. The two interactions, energy interactions, which you can have between surrounding and system is work and heat. So what is thermodynamics? We are now in the proper state. This one we can tell the definition of thermodynamics, nothing but the study of the change in the properties of the system by the interaction of heat and work between system and surrounding is called thermodynamics. I'll repeat it. You can write it down. The study of the change in the properties of the system due to the heat and work interactions between the system and the surrounding is called thermodynamics. How much heat you will supply and how much temperature will change, and how much volume will change, and how much pressure will change. Okay, all those kind of calculations and studies we are doing in thermodynamics. Okay, so please note all these things and raise your hand, then we can go ahead and start the chapter formally. Okay. Okay, have you noted? Again, I repeat the definition of thermodynamics: the study of change in the properties of the system due to the interactions, heat and work interaction between system and surrounding is called thermodynamics. Okay, so note it down and raise your hand after that. Okay, all these things, what I have written on the board also. Okay, now, so this is thermodynamic definition, everything. Now we will see the next topic. Okay, so first topic is over, system and surrounding. The topic is over. Now we will talk about closed system and open system and isolated system. It's very simple only. Closed system, open system, isolated system. Suppose you have a system which is called closed system, means that means a container with a closed lid having certain gas inside it. This is called as a closed system. But it's exchanging the heat between system and surrounding. Heat and work interactions are allowed. Heat and work interactions are allowed. It can exchange the heat between system and surrounding, and even you can supply the work like this, but no exchange of mass. The gas which is inside the system will remain inside the system only. Okay. No exchange of mass. Only heat and work interactions are allowed. Mass interaction is not allowed. Gas cannot escape out or gas cannot be inserted in. That kind of system is called closed system. Open system means even the mass can enter inside or can leave, for example, and even the heat and work interactions are also involved. Heat and work interactions are also allowed. That is called open system. An isolated system means you are going to isolate it like a thermos flask where neither the heat interaction, work interactions are allowed and nor the mass transfer is allowed. So that is called isolated system. So you can make it like this: open, closed, isolated, heat and work. Sorry, heat and energy interaction and energy and mass. Okay, energy and mass. Open means both are okay. Closed means energy okay, mass not okay. And isolated means both are not okay. Okay, note it down and then I will tell you the next topic. Okay, so isolated system, open system, and closed system is over. Okay, note it down please and raise your hand. Okay, noted now. Okay, shall we proceed? Noted, Nishant. Now, what is the next topic? The state of the system. Let's talk about the state. What is the meaning of state? And I already explained you what is the state of the system. State means something which is a predefined. Something means where the properties are in the equilibrium. When the system is in equilibrium with surrounding. Now, before that, I should define the equilibrium, right? So, what is equilibrium? Spelling and all, you leave it here. I don't know all these things. Equilibrium and all. Equilibrium. So, the three types of equilibrium are there actually. One is mechanical, one is chemical, one is thermal. That means when the temperature of the system is equal to the temperature of surrounding, that is called thermal equilibrium. When the pressure of the system is equal to the pressure of the surrounding, it's called it is in mechanical equilibrium. System is in mechanical equilibrium with the surrounding. When the rate of forward reaction is equal to rate of backward reaction, then we say that system is in chemical equilibrium with the surrounding. Okay. When the system is in all the three equilibrium with the surrounding, then it is said to be in thermodynamic equilibrium with the surrounding. System is said to be in thermodynamic equilibrium. When all the three equilibrium are existing, the system is said to be in thermodynamic equilibrium. Basically, there are three types of equilibrium: thermal, chemical, mechanical. If temperature of the system is same as temperature of surrounding, it's called thermal equilibrium. If rate of forward reaction equal to rate of backward reaction, that is called chemical equilibrium. And if pressure of the system is same as pressure of surrounding, I give you an example how this equilibrium is established. Suppose you have some weight kind of thing here and some gas here. Now what's happening is that in this case, suppose initially what will happen, the gas will expand maybe, and the piston will go up and will stop. Okay, maybe you're heating the gas or something. So gas will expand and will stop at certain place, right? At that place, you can say that whatever the pressure of the system which is being applied on this piston, suppose the system is a gas, first you have to define the system. So that pressure of the system is same as the pressure of the surrounding. The surrounding pressure is atmospheric pressure plus the weight of these objects. That system pressure, if it is equal to the surrounding pressure, then there will be a mechanical equilibrium between system and surrounding. Likewise, the gas is heating, right? And suppose some temperature of the gas, initially the gas may be at 100 degree and outside surrounding may be 50 degree, but after some time there will be exchange of heat between the gas and the surrounding, and the gas will also come at 50 degree and the surrounding also will come at 50 degree. So the temperature of the system will become equal to the temperature of the surrounding after some time. So the system is said to be in thermal equilibrium with the surrounding at that point of time. Okay. So you are seeing that yes, after some time the system is in thermal equilibrium and mechanical equilibrium and chemical equilibrium. So you can say that yes, the system is in thermodynamic equilibrium. You know, so there is no change in the properties after that. The properties also become somewhat constant. So that is called one state of the system. State of the system. When state of a system is defined by certain value of the properties. If you say a happy state of your face, means there will be measurable smile on your face, measurable size of your eyes, measurable the size of the nose. So all the properties will be defined, right? And that will define a state of the system. Suppose I slap you, means if I do work on you, then your state of the system will change. Why it will change? Because the properties will change. So the concept is that whenever there is a work or heat interaction between system and surrounding, it will cause a change in the properties, and the change in the property will cause a change in the state of the system, because state of the system is defined by the properties of the system. Okay, so whenever there is a work and heat interaction, will change the properties of the system, and change in the property of system will cause a change in the state of the system. Is it clear? Can you note it down, please, all these things? Then we can go ahead. Okay, note it down, please. Okay, now clear na state of the system and all. Hmm? Now I'll talk about the work and heat. Okay, something I will tell you about work and heat. This is what thermodynamics is being taught like this only. Okay, the best way it can be taught. So we are discussing one by one, and now we are totally inside the subject. Slowly we are getting inside the subject. Okay, now I talk about the work and heat to view. Okay, what is the difference between work and heat? Both are the forms of energy. Both are different forms of energy. Both are the forms of energy. Heat is a form of energy. Work is a form of energy. But both are the forms of energy in transit. Transit. In transit means these are those things which no one can hold. You cannot have the work. You cannot have heat. You can never say that I am having 100 joules of work. Wrong. You can say I am doing, I have done 100 joules of work, or I am doing some work. I have done that 100 joule work. That means this work done or doing or transferring, that is important. Not having. You cannot have the work. You cannot have the work inside you. Okay. You cannot say that I have 100 joules of work inside me. You never say like that. You always do the work. And likewise, you can never say you have 100 joules of heat inside you. Okay, that's wrong statement. You can only say that you have given 100 joules of heat to someone. That means some transfer of heat has happened from high temperature to low temperature. Okay. Heat transferred. Heat cannot be contained. Work cannot be contained. These are the forms of energy in transit. Then what? This the energy which you have inside you, that is called internal energy. That is called internal energy. The energy contained in a system in the form of vibrational energy or kinetic energy or potential energy or magnetic energy or electrical energy or any form of energy inside your system, which is contained in the system, which is possessed by the system, that is called internal energy. And work and heat are not internal energy. These are different forms of energy which are in transit, which can happen between system and surrounding. Okay. The transfer of energy between system and surrounding will happen in two forms, only and only in two forms, either in the form of work or in the form of heat. Okay. Now, how work transfer will take place and how heat transfer will take place. Okay. Heat transfer takes place from high temperature to low temperature, or by burning something and you are transferring the heat from that thing to the system. Work transfer will take place by compression or expansion. Okay. By the volume change. Okay. If you press something, you are doing the work transfer. That means there should be some displacement and some force. And force into displacement is work transfer. Okay. So work transfer will happen basically by displacement, and heat transfer will happen by the transfer of heat from high temperature to low temperature. Somewhat it is clear. You write it down, then I will explain you some more ideas I will give you about heat and work. Okay, just wait 5 minutes. Okay, I will come back. 5 minutes, please wait. Okay, both are there now. Ellen, Nishant, you are there? Nishant? Ah, okay. So, the third form of energy, first is heat and work. Both are energy in transit. And the third is the internal energy, which is the energy contained by the body. This is also two types. Internal energy are of two types: microscopic, macroscopic. Microscopic means molecular level. Molecular level, there will be some vibrational energy, some magnetic energy, some chemical energy, some kinetic energy, some potential energy. So many forms. At the molecular level, each molecule will possess, and you have to summate all those energies. That is called microscopic internal energy. Macroscopic means as a system, as a whole, will have certain kinetic energy and will have certain potential energy. Like it will have certain position as a system, all the molecules together, and all the molecules together may be under motion together. That is a form of kinetic energy. Entire molecules as a system. That is called macroscopic form of internal energy. And microscopic plus macroscopic, that is a total internal energy. Okay. Generally, macroscopic kinetic and potential energy will be zero. So we are talking about microscopic form of energy. Mostly the system will be under confined system in thermodynamics. And if it is a confined system, its macroscopic kinetic energy and its macroscopic potential energy will be zero. Only microscopic energies will be there. Vibrational energy, magnetic energy, chemical energy, kinetic energy, potential energy, microscopic one. Okay. This is called internal energy. Now what is happening is that there is a, so this topic is over. Okay. And then now what I'm telling you is I want to just tell you about the last thing, and then we will come to the mainstream. The last thing is the process, the process of beating you, the process of making you happy, the process of teaching you. Okay. So when that you are doing certain process, that time only you are interacting with the system and surrounding. How the system and surrounding will interact, there must be some process for doing it or not. How I will slap you, there must be certain process. I will beat you hard, or I will beat you soft, or I will tear you off. Okay, whatever I want to do, but there is certain process, right? So what kind of process we are talking? Not talking about beating process, we are talking about thermodynamic process. Thermodynamic process, that means how you are going to do the work or heat interaction. Okay. So there are various types of process. Okay. Process is nothing but it is the way in which you are going to interact with the system and surrounding. That is the process. And by doing that process, definitely the properties of the system will change, and properties of the system will change, the state of the system will change. Okay. So these are all interlinked terms. What are the interlinked terms? The state, properties, process. These all the three things are what? Interlinked with each other. When you do certain process, the property of the system will change, which causes the change in the state of the system. Am I correct? When I beat you, your properties changes, which change causes the change in your state, happy state to sad state, like that. Okay, clear? So process is clear or not? Process is the method where which causes the change in the properties of the system. Okay. So note down all these things and then I will tell you about various kinds of process and those things. Okay, we'll go in depth. Okay. So mainstream of the thermodynamics will start now. Okay. Note it down and tell me if it is clear. Note it down and raise your hand. Note it and raise your hand. Different types of energy, microscopy, macroscopic, internal energy, heat and work, everything. Note it down. Okay, over. Nishant, written. Written, Nishant. Noted here, huh? Okay, so see, I will tell you now. See about heat. So what is that? Now you think about it. What are the different types of process? Now process are of two types. Okay, two types in thermodynamics: reversible and irreversible. This is one category categorization. Okay, reversible and irreversible. Now this is very deep concept. Reversible and irreversible means simple only. See, reversible process means the one which you can reverse it without causing the change in the whatever happened. Means I give you a simple example. You want to go from this point to that point. Okay, so you have to do the walking process, right? So if you want to go from this point to this point, suppose you are running or fast walking you are doing, and you go from here to here, and if I ask you to reverse the process, it's very difficult. Means exactly repeat the process, reverse it like a movie. You're reversing, what do you call it, playback type of, no, not reverse. Okay, going like this, you go on like this and come back like that in the same manner. It's very difficult if you go by running or fast walking. Okay, so that is not a reversible process. Running is not a reversible process. Anything which happens fast or quick, that is not a reversible thing. Okay, reversible thing has to be very very slow, so then only you can reverse it. For example, a slow walking process, a step by step walking process, you can always reverse it easily. You can reverse it, am I correct? You can reverse it also. It will take a long time, but you can reverse it. So it is slow and it is step by step. The step by step means what? Step by step means when you go from one step to another step, you are going from one state to another state, right? And each state is a predefined properties of pressure, volume, temperature. So it's an equilibrium state. There are two types of states actually. I forgot to tell you. There are two types of state. Equilibrium state. Equilibrium state means That means pressure, volume, temperature of the system is same as pressure, volume, temperature of the surroundings. So when you are going from one state to another state, if you are in equilibrium state, you are going step by step, slowly. Okay. That kind of process is called reversible process. Irreversible process means the states which are coming in between, those are non-equilibrium states. In those situations, the pressure, volume, temperature of the system is not same as the pressure, volume, temperature of the surrounding. And in that situation, it's very difficult to reverse the entire process in the same manner. Okay. So that it becomes irreversible process. That means it is a fast process. It's not step by step. It's a continuous fast process. Okay. Okay. I will give you an example to explain you what is the, in fact, reversible process is not possible. It's not possible. And this is a real process. Irreversible process is real. All the activities in our life are irreversible process. It's not reversible. Okay. So I'll give you an example how it happens actually. And one more thing, that reversible process, there is no friction. It happens slowly. There is no friction and no viscosity. Okay, all those things. But in irreversible process, friction, everything, viscosity is involved. Okay, and it's a fast process. Okay, understand? Somewhat you write it down. Then I will tell you more about reversible and irreversible. Note it and raise your hand here. Noted. Helen, Nishant, note it and raise your hand. Okay. So I give you an example. How to do this process reversibly and how to do it irreversibly. If you want to do irreversibly, that's a real process. No need to do anything. Just keep the hot cup of coffee in the normal surrounding. Surrounding is at 30°. Coffee may be at 90°. Slowly or fastly, whatever you call it, as such it is fast only. The temperature will drop from 90 to 30. After some time, the coffee is also 30°. Surrounding is still 30° because it's air only. Or maybe 31° and this also 31°, something like that. And it's over. This is called irreversible process. Okay. If you want to do it reversibly, what you need to do is, the important thing is every state uh, state of the system in the process must be an equilibrium state. Equilibrium state means the pressure or temperature, whatever, of the system must be equal to the surrounding. Now that's not possible here in the this what in the first scenario, because the surrounding is at 30, system is at 90. System will go from 90, 89. Okay, system will go from 90, 89, 88, 87, 86, 85, 84. All these states are non-equilibrium states. Why non-equilibrium states? Because these states, the temperature of system is not at all equal to temperature of surrounding. Temperature of surrounding is 30 degree, but temperature of system is 80, 89, 88, 87, 86, 85, 84, 83, 82. So there is a huge difference between temperature of the system and temperature of the surrounding. Actually, if you want this process to be reversible process, then each state of the system, the temperature of the system should be equal to temperature of the surrounding, or very, very near to the temperature of the surrounding, extremely near. Then only you can approach the irreversible to reversible process if you wanted to make it reversible process. Okay. So this is the situation. What you are observing here is that the states undergone by the system are non-equilibrium states. Now, how to make it reversible means, if you want to cool the cup of coffee from 90 degree to 30 degree, what you need to do is, first 90-degree coffee, you place it in a bathtub or any tub, not a bathtub, but any kind of container, which is at the temperature of that container should be exactly 89.99999, something like that. Very, very close to 90 degree, but not exactly equal, because if it is exactly equal, there won't be any heat transfer. Now, what will happen, that there will be a small amount of heat transfer. Okay. Small amount of heat transfer between the system and surrounding, immediate surrounding. This may be having a water bath or something. And the system will come also at 89.999. And the surrounding is also at 89.999. Now, in this is the first equilibrium state of the system. Okay. And that's the equilibrium, because system temperature is equal to surrounding temperature. Now you reduce the temperature of surrounding by again point to some degree, 98 like that. And again the system will undergo another equilibrium state, and it will again another small amount of heat transfer will happen, and system will come to 89.98. Likewise, you have to do it lakhs and lakhs and lakhs of time, finally to reach final container, that is 30.5, and this may be 30 degree. Then there again finally small heat transfer will take place, and finally you are reaching from 90 degree to 30 degree. But it took a lot of time. Okay. And in this process, all the states undergone by the system are the somewhat like a equilibrium states. So this kind of process is called reversible process. Okay. So this is how the difference between reversible and irreversible. Now it's clear. Thermal means it's clear what is reversible and irreversible. Somewhat it is clear, at least from the exam point of view. Okay. And second thing, that in reversible process, you are seeing that difference in the system temperature and surrounding temperature is very, very small for each transfer, heat transfer is being taken place. Okay. So whenever you are seeing that system temperature in the normal life, it won't happen, right? It won't be like this. In normal life, it will be like this only. In routine life, for all the activities, you will see that always there will be a huge difference between system temperature and surrounding temperature, system pressure and surrounding pressure, right? So that is, there is very difficult to perform the processes in a reversible manner. Okay, mostly the process will happen in an irreversible manner only, like this. Okay, understand? Even when I ask you to run from one point to another, means you will go fast only, right? You won't go by step, and each time is making the equilibrium states and all, right? And one more thing, that whenever you do you do any kind of work reversibly, it involves least amount of work is required for doing the thing in the reversible manner. Least work. If you're working very, very slowly, it involves a least effort. Okay. But it will take a long time, but effort required is least. Okay. So this is also another concept, that if you do anything reversibly in a reversible manner, then it involves least work. Okay. Maximum efficiency. maximum efficiency, but time involved is very high, but efficient, very efficient. Okay, clear? Note it down, and then we will go to the next topic. Okay, note it down, please. Raise your hand after noting it. Okay, Nair. Understanding. I will list down. If you want, I will make some points for you. Okay, so that you can write down properly. Okay, just you write few points like that. That means delta T or delta P, whatever. This should be infinitesimal, means very small for reversible process. Okay, and second thing, it's very time taking, long time. Third thing, it's most efficient. Fourth thing, that all the states which are undergone by the system during the process, are equilibrium state. Okay, and fifth thing, this is not possible. Okay, all these things are for reversible. For irreversible, these are the real process. They have finite difference in temperature between system and surrounding, and pressure between system and surrounding, and the states are non-equilibrium states. States undergone are non-equilibrium states, and these are possible, very well possible, and happening all the time, and they are less efficient. Okay, and they take time. They don't take time for happen. Okay, they can happen in finite amount of time. Okay, normal times. Okay,
Note it and tell me here, okay? Note it now, then we'll go ahead. Noted. Okay. So this is what, and one more thing that you can even, so I will give you one example, what are different types of process. And one more thing that you can always plot the process in a graph, like a PV graph, pressure volume graph. I give you one simple example, the heating process. Suppose you are heating it. So the pressure inside the system, what is pressure? You know, all the particles are vibrating all the time now. They will strike the surface with certain amount of force. That is only the pressure of the system, force by area. So when you heat it, it will expand. So volume will increase and pressure will reduce. Okay. So the graph will be like this. First, this is the first point, this is the second point. The pressure here P1 V1, here the pressure is P2 V2. You can see that volume is more than volume 1 and P2 is less than P1. This is the expression of this process. This is process. Now the process could have happened in several ways. You want to go from the state. This is called state 1. This is called state 2. You want to go from state 1 to state 2. So there are several ways of going from 1 to 2. There are several processes. You can go like this. You can go like that. You could have gone like this. You can go like this also, 2 process. Okay. So there are several ways of going from 1 to 2. That's why there are several processes for the change of the state. Process means change of state. Process means change of state. Now this change of state can be done in several manners. Like this, like this, or like this, or like this, in a reversible manner or irreversible manner. That can be represented in a graph. How this change is happening, right? Okay. So this is what a graph and all, and how the process is changing. What are different types of process? I will explain you. Okay. Different types of process I will explain you. Before that, I want to, if you have noted all these things, I want to explain you one more thing, and that is point function and path function. Point function and path function. Point function is also called a state function. State function and path function. See, the internal, all the properties and internal energy. These are point functions or state functions. I'll explain you. And heat and work. Heat and work. These are path functions. Because these are the energies in transit, right? These are the energies in transit. So they depend on transit. Means depend on the path. How much, what path we are following. Accordingly, heat and work requirement will be different. But these properties like pressure, volume, and temperature and internal energy are the state function. They depends on the state, which state we are in. If we are in this particular state, the values will get fixed. P1, V1, T1. If you want this particular state, the values are fixed. P2, V2, T2. Okay. That is a state function. Does not depend on the path. But heat and work depend on path. How we are going like this, or we are going like this, or we are going like this, or we are going like that. So depend on the path followed, amount of the heat and work interaction will be different. But the properties and the internal energy, they are state function. Okay. State function means they depend only on the particular state. You want in a happy state, you need this much pressure, volume, temperature. You want sad state, you need this much value of the properties. Okay. But how to bring a happy state and how to bring a sad state, for that amount of the work required may be different depending on the amount of the what kind of process I am following, whether I am following some process or heating process or beating process, whatever process. Okay. So this is the difference between state function and path function. Note it down. What are the different state function? Means pressure, volume, temperature, internal energy, all are state function, and work and the heat are path function. Note it down, please. Note it and raise your hand, please. Okay, noted. Okay, now. So now what else here? Actually, I will tell you this chapter has come to an end. Okay, end means you will say what is that, sir? What you're telling about? Anyway, I tell you one more thing that I want to talk about first law of thermodynamics. This is here the conservation energy law. Conservation of energy only. Conservation of energy. One thing I want to tell you that if this is a system now, one thing I want to tell you, if it expands, maybe it will expand because of heating or something. Just like think about a balloon filled in with air, and if you heat the air, then the balloon expands, right? Basically, the system is said to expand. That means you are supplying the heat to the system, and that heat is getting converted into work because there is a displacement of the, this is called boundary of the system. Okay, boundary. So system is expanding because boundary is changing. So system expands, right? Because of heating. So basically, heat is getting converted into work. Am I correct? And also at the same time, heat is also, you will see that there is a certain amount of increase in the temperature of the system, right? Temperature at the same time, the gas will get heated also. So heat is getting converted into work, especially the heat temperature of system is increasing. Temperature is increasing means vibrational energy of the system is increasing. Particle starts vibrating at a faster rate, and that is called as internal energy, right? So whenever temperature is increasing means internal energy of the system is increasing. So whatever the heat you are giving, that is converted into two ways. One is that it is expanding the system. That means some heat is getting converted into work, and some of that heat is actually increasing the temperature of the system. That means internal energy of the system also increased. So here we can account the energy. We are doing the accounting of energy. We are doing the accounting of energy because energy cannot be created nor destroyed. It can be only transformed or transferred from one form to another, right? So we are giving, now if we are doing the accounting of energy to the system as a whole, we are giving the energy to the system in the form of heat. We are heating the balloon, and that heat is getting converted into two forms. One is that it has converted into work. That means system is expanding, so that is the work. And some amount of heat is getting converted into temperature increase. That is internal energy of the system is increasing. So this type of interaction between three quantities, heat always, there will be heat, work, and three things only will be there. Okay, so this type of accounting of energy is taken care in the case of first law of thermodynamics. Okay, conservation of energy. Okay, understand? Understand or not? So this once you write it down, and then I will come to the basic first law of thermodynamics. I will state it, and I will tell you about the sign convention also. Okay, then you can solve the questions on thermodynamics. So first law also. Okay. So first law will get over if you note it down. Okay. Note it down, please. So what is first law of thermodynamics? It's basically law of conservation of energy. Energy can neither be created nor destroyed. It can be transferred from one form to another. Now, basically here in this case, I told you an example of a hot air air in the balloon, and we are heating it. So we are giving some energy, and that heat is getting transformed into work and internal energy. That means the system is getting expanded. So work is being done by the system, work is done by the system, and heat is taken by the system, and temperature of the system is also increasing. Okay. So this kind of accounting of energy is called first law of thermodynamics. Okay. Note it down, please. Note it and raise your hand, please. Noted. Okay, noted now. See, I will now tell you about the sign convention. Remember, heat, now system, heat given to the system is called positive. Heat rejected by the system is called negative. Work done by the system, that means expansion, that is positive. Work done on the system, that means compression of the system, on the system by the surrounding, that is called negative work. Okay, these are the four things which you have to remember. Heat given to the system, that is positive. Heat rejected by the system, negative. Work done by the system, positive, and work done on the system is negative. Okay. Easy way to remember is that when you talk about heat, then you think that means if system is getting, it is positive, if system is leaving, it is negative. When you talk about work, it is reverse. When the system is doing work, it is positive, and when system you are doing the work on the system, that's negative work. Okay. These four sign convention you have to remember. Just note it down and remember it, and then I will explain you the first law of thermodynamics. Okay. Four lines you have to write. 1, 2, 3, 4. Heat given to the system is positive. Heat rejected by the system is negative. Work done by the system is positive. Work done on the system is negative. Okay, like that. Heat given to the system is positive. Heat rejected by the system is negative. Work done by the system is positive. Work done on the system is negative. Heat given to the system is positive. Heat rejected by the system is negative. Heat work done by the system is positive. Work done on the system is negative. These four things you have to remember. This is called sign convention for the first law. For the first law of thermodynamics. Okay. What is first law? First law is the law of conservation of energy. Okay. So please note it down and raise your hand, please. All these 4 points. Did you have you noted? It is not about formula or theory here. Who is asking? Ellen. No, it like that here. It's not about theory or formula. It's about understanding. Without understanding, you cannot solve anything. Okay. It's a concept based. There is nothing like theory or formula based in this one. And JE and all, these are not like nowadays. Not like that. The formula, you put something in the formula and answer will come. Without understanding the concept, thermodynamics totally very deep concepts. If concepts are not clear, means nothing, no answer will come correct. All answers will come wrong. Even if you know the formula also, you cannot get any answer out of it. Definitely no answer will come correct. Okay, so concept if not there means zero result. Okay, that is the problem. That's why most of the people are not able to crack JE other exams, competitive exam. They don't understand. Nowadays they cannot even do the 12th class also, because now 12th also is like that only. They will ask only, they want to know that really whether you know the topic, or you are mugging up some formula and trying to put substitute in that formula. Definitely it won't work. Okay, so you have to focus on understanding the things. Formulas are naturally should come out from you. Okay, like I could have told you this first law of thermodynamics. You know what is the formula for first law of thermodynamics? This is the formula. But if I write it like this, some of your school teacher will teach like this. They will write like this and they will tell this is the formula, and the question will come, and in the question you have to see whether heat is there. You put the heat value here, you put the work value here, and you put the change in the internal energy here, whatever this is, change in internal energy, and you will get the answer. It's not like that. Okay, if you are not understanding the things properly, it won't work out and the answer will not come correctly. Okay, so there is no need of mugging up the things. Understanding the things only will help you. Okay, you take it in point today, from today until last of your academics. Never ever try to mug up any kind of thing. Okay, better don't think, don't do that subject or leave that subject. or get failed also. But don't mug up anything. Okay. Now you please understand. Here I have not written in this formula. I have not written delta in front of Q. I have not written that. I have not written delta in front of W because these are path functions and they are not change. It's not that heat of the system will change or work of the system will change, because heat and work does not belong to anyone. Heat and work are in the process. If you are going from process 1 to 2 or state 1 to 2, then we can write like this: Q1 to W1 to. That means when you are going from 1 to 2 state, this much heat is transferred, this much work is done. This is the formula for your first law of thermodynamics. What is Q, what is W, and what is this one? Q is nothing but heat. Heat transfer either to the system or by the system. Means that means it can be positive or it can be negative, depending on whether it is given to the system or it is rejected by the system. Work done by the heat transfer in the process 1 to 2. Work done by the system or on the system in the process 1 to 2. It can also be positive or it can be negative. If the system is getting compressed, it will be negative. If the system is expanding, it will be positive. Okay. Work done in the process 1 to 2. And change in internal energy means final internal energy of the system minus initial internal energy of E final minus E initial. This is called change in internal energy. This depends on temperature mainly. Depends on temperature. Okay. So this is the formula for first law of thermodynamics, where you have to follow the sign convention which I taught you. Okay. Q1 to 2 is equal to E2 minus E1 plus W1 to 2. Okay. This is the formula. Okay. Note it down. This is the first law of thermodynamics. For closed system, thermodynamics for closed system. This is not for open system. This is for closed system. Okay. This law means there is a first law for open system also, separate formula for that, but not this formula. This formula you should use only for closed system. Okay. Closed system means where there won't be any transfer of mass, only transfer of energy will be there. Okay. So if you have noted it, you please raise your hand. Noted. Okay. You understand the first law now? We'll do the numericals later. Okay. Numerical very easy only. Once you know this concept, just you have to put the values only. Okay. So these are all things. So many things we have discussed there. Okay. Slowly that concept will develop. It won't happen in one day. Some time is required to absorb the concepts, and many things are there. Okay. It's not like that. But many basic things I have put inside you. Okay. Now. So now this is just all the foundation is very proper now. Somewhat I understand. Somewhat foundation is okay. At least first law, till first law it's okay only. Okay. Half of the chapter we have done. Okay. So many things are there. Actually, they have put one full subject in one chapter. Okay. So many things, small topics are there. We cannot go in very depth, but we can understand those things. Okay. So many things are there now also. Second law of thermodynamics is there. Third law is also there. Okay. So we can say that we have done up to page number first 6, 7 pages we have completed. Okay. Okay, so we have one more class here, one or two more classes. Today itself we'll have one more class. Okay, I will inform you timing. Meanwhile, next 2 hours or 3 hours, you please complete whatever I taught you, the notes you please make and send to me, especially that thermodynamics. Okay, that fluid mechanics also, whatever questions I have taught you, please make the notes for that, solve it, get the final answer and submit me. And this one also, thermodynamics also, whatever I have taught you, make the notes and submit it. Okay. So after that, I will conduct today one more class. Okay. So I will inform you the timing. If you have any constraint, you message me. If you are not available in particular timing, I will inform you. Okay. I'll convey you and ask you to attend the class. Okay. Okay then. Now I am closing the class. Okay. Okay. Bye.